and plug it in. Okay, great. No harm because no technical definition yet. So let's define convergence. Right? So here's the idea. If I want some number to converge to zero, I want that the sequence eventually is only so let's say there's some number half. I want the sequence to eventually be always half around zero, right? So I eventually it should happen that every term of the sequence is between minus 0.5 and plus 0.5. And then later on, eventually it should be between minus 0.1 and plus 0.1. And then no matter what positive number you give me, eventually it should be in that range. Right? So no matter what positive real you take, eventually all terms of my sequence should be in this interval. And that's what convergence means. Because in the long run, all terms of a sequence are at most this much away from zero. So that's what we'll formalize. Sequence. So it's all real. So just focusing to converge to N if so there will be a lot of quantifiers, so be careful there. If for all positive reals epsilon, there exists. Remember, we want that eventually all terms become all terms are at most L plus epsilon and at least L minus epsilon. So there exists a natural number n such that the absolute value of the difference between an and n is less than epsilon for all n more than n. It doesn't matter if there are inequalities. Not restricted. Fine. So let me know if this makes sense.
Yes. Yeah.
This is crucial, so do ask me questions right now. So, what is this really saying? That it's saying, like, pick an epsilon. I can show you an n. Okay, so this might be confusing, so let me use n naught. Maybe an epsilon is the Okay, so no matter what epsilon you give me, positive real, I can show you a natural number such that all sequences from that point onward, that is all terms whose index is at least as much as n epsilon, are no more than epsilon away from this L. And so and it converges. So yeah, questions, please ask me right now. We also denote it as an tends to L, or we also say the limit of an as n tends to infinity is L. These are different. We also sometimes say lim an is L. I mean, I generally don't use this, but some books do. This is convenient, sort of. Sometimes people just write the index here. Yeah. Lots of notation. It'll be clear. Really. Okay. So let's do an example first. So let's look at this again, and we want to show formally that this converges to 0. So using this definition, can you prove that this converges to 0? So
Yes.
yeah, it's not too hard. So we can sort of just work backwards, right? So okay,
We can
someone
use the
gave
inequality.
yes. So someone gives me an epsilon more than 0. All I need is to find an epsilon such that this is true. So let's just write it in a different way. So for this question, what is this? What is this thing? It's just saying 1 over 2 to the n minus 1
N minus, yeah, minus 0.
minus 0 is less than epsilon. And then this is if and only if 2 to the n minus 1 is more than 1 over epsilon. This is if and only if n minus 1 is more than log base 2 of 1 over epsilon. And this is if and only if n is more than 1 plus log base 2 of 1 over epsilon. So this means if I pick any n epsilon which is greater than this and it's a natural number, then I'm done, right? So I can just pick n epsilon to be. I don't have to be strict, right? I can choose it to be 10,000 plus ceiling. Mod. It's fine. This is certainly more than this. So that's it. Enough. I thought this no that this will imply this. So that's the direction we want. This was just to work out what I should choose an epsilon as. Is this clear?
Yeah.
Yeah.
Just waiting for someone else to ask about. If it's clear, then it's great. Okay, so it is clear. It seems. So try this one. I have a sequence where an is I hope everyone knows what sine is. It's just sine n over n plus 1.
N is in radians of obviously, right?
Your wish, but yeah, but yes, we do. You can choose degrees, it's fine. It doesn't affect the answer.
Converges to what we have to prove.
Yeah, I mean, often you can guess the limit. In this case, you should be able to guess the limit, but
0.
yes. Yeah.
If epsilon, I got the solution. Shall I say?
Wait for that.
I have also got the solution.
Okay, awesome. Okay, Pranav.
Yeah. So if epsilon is like greater than 1, then this thing is always less than 1, so it's fine.
Always.
Yeah. So now if epsilon is less than 1, we can just like n to be somewhat like 10 plus greatest integer function of 1 by epsilon, and that works.
Yes. Okay. Yes, this works. Yeah, exactly.
Because like sin n is always less than 1, so if we just take the maximum value 1, then this thing is just greater than epsilon.
Yes. So this less than equal to epsilon is the same as saying um, sin n over n plus 1 less than equal to epsilon. And note that we don't want an implication. We care more about the reverse implication. So because we're sort of working backwards, right? So we can't just magically, usually we can't just magically think of an epsilon. So we sort of work backwards and see what works. And so note that since this is less than equal to 1, this implication holds. That if this is less than equal to epsilon, then so is this. Right? So this is the same as saying n is at least minus 1 plus 1. Right? And so this will help. Okay. So not too difficult, right? So it's nothing crazy so far. And then there are these properties that that you can prove, like if you have two sequences and V1, V2, then let's say this converges to capital A, and this converges to capital B, then the sequence, which is like the corresponding sum of terms, A2 plus B2, converges to A plus B. You can sort of try this out. Actually, let's just try this out as well. It's formally, how do you show this? It's sort of these set of obvious properties which we are trying to formalize so that we can formalize harder things eventually. Yeah. So do this.
Can I tell you how to do this?
Sorry, what?
I think I can tell.
Yeah, tell me.
We need to have that some for some n or modulo an plus bn minus a plus b is smaller than some epsilon, some given epsilon greater than 0.
Yes.
Okay. So we can have that modulo an minus a plus modulo bn minus b is greater than this thing that is given.
Yes. So if this is true, then so is the original.
Yes.
Yeah. Good.
and we can just add that modulo n minus a is also smaller than some epsilon, and modulo b n minus b is also smaller than some epsilon. Then we can, if we have some if we have some epsilon, then we can take any value of a n and b n such that they go smaller than epsilon by 2.
We can just directly say from here that the first one is less than equal to epsilon by 2 also, and second is epsilon by 2.
Yes, that's what I
Yeah,
Yeah.
yeah. Right. So, okay. So instead of trying to do that, we can simply say that this follows if I can choose an n such that these are both less than equal to epsilon by 2. And now that's easy, right? Because I can just choose the corresponding n epsilon over 2, which is guaranteed for this because it says that this converges. And then there's a some n prime epsilon over 2 from this. And then we can just take the
we
maximum.
can take the greater also.
Yeah, or we can also take the sum, whatever.
Yes, but the greater will be nice.
Questions? Okay, great. So there are some other properties like this, such as product or something, which I think I can just make a list of those. And okay, um, just looking for more such things. Okay, great. Yeah, and then we can talk about subsequence. We have a sequence with this, and a subsequence is simply uh, a subsequence is simply just pick some subset of elements here. Something like this. So we sort of just skip elements. This is a subsequence. That's really the definition. And let's say this is an infinite subsequence because this never ends. And we'll only look at infinite subsequences. We'll not consider finite subsequences. Okay. And now if a sequence converges to so if and this subsequence itself is sort of like a sequence, right? So I can write this as the first number. This is my second index, third index, fourth index, etc. Really bad. Okay, so now, the point is that if a sequence converges, to A, then the subsequence also converges, right? This is clear, right? Does this make sense? Yeah.
Yes.
Okay. But obviously the converse is not true. Like, can you just give me an example?
So the elements which are like removed from the original sequence, we can just take it like let's say the subsequence converges to A. We can take the big elements like 100A, 1000A, and so on.
Yes, something like that. So just take this subsequence to be a constant sequence, let's say 1, 1, 1, 1. And then I can just put 2, 3, 4, 5, 6, 7, 8, 9, and this doesn't converge to anything. Okay, great. So I just wanted to define subsequences here. And okay. That's because when we look at problems later, I don't want to define it later. Okay. Finally, I also want to talk about Cauchy sequences so that we have a problem to work on after this. We have a sequence A1, A2, A3, etc. The sequence is said to be Cauchy if, so think of this as a question actually. Cauchy if for all epsilon more than 0, there exists an n epsilon such that for all m comma n more than n epsilon more than equal. The difference between am and an is less than equal to epsilon. Let's read what is written here. So what I'm saying is that
Such a sequence can never converge, right?
let's read the thing carefully. Yeah. So here's what I'm saying. So the sequence is Cauchy if no matter what epsilon you pick, eventually all terms are epsilon close to each other, right? That's what it's saying. So it's saying that no matter what epsilon you pick, there is some natural after which all these terms are no more than epsilon away from each other. So, for example, this sequence, the same sequence before, the standard example, 1, 4, 1, 8, etc. This is Cauchy, right? This is Cauchy. Because let's just pick some random n for now. So after, if this, so this n corresponds to the term 1 over 2 to the n minus 1, then 1 over 2 to the n, etc. And the difference between 2 to the n minus 1 and 1 over 2 to the n minus 1. So this is n is okay. So let's say n is less than m, then this is definitely less than 1 over 2 to the n minus 1. In turn, is less than 1 over 2 to the n minus 1. And so this will be less than epsilon if I choose an appropriate n epsilon. Right? So this is Cauchy. So here's what you want to prove. So prove that a sequence of reals is Cauchy if and only if it converges.
Okay, I got that. Cauchy sequence is converging. Shall I tell?
Convergent sequences or Cauchy is easy. Cauchy sequences convergence hard.
Yeah. Oh yeah.
One side is easier.
Yeah, I got a converging sequences Cauchy.
Yeah. So convergent convergent sequences are Cauchy is the easier side. So try the harder side actually.
Can you scroll up a bit to the definition of Cauchy?
Yes. So remember, convergent sequences mean that for any epsilon more than 0, eventually your epsilon close to the limit. And Cauchy means for any epsilon more than 0, you're eventually all terms are epsilon close to each other. So that's the difference. So convergent implies Cauchy is sort of easy in the sense that if you're epsilon close to a fixed point, then you're at most 2 epsilon close to each other, right? By triangle inequality. So that's how you prove the first one. The second one is trickier. This will take time, so it will take you time. We'll spend a lot of time on this.
I guess I have some progress.
What?
I guess I have some progress.
Okay, yeah, tell me.
So by the definition of Cauchy, we have that for some n epsilon, a natural number n epsilon, we have m greater than n epsilon, so that also we have modulo m minus a n is smaller than or equal to epsilon.
Yeah.
So we can add in that modulo plus a minus a.
What is A?
A is some just it is what is happening. Sorry.
Okay, maybe before this we should have discussed bounded sequences first. I think that would have been a good idea. Yeah. Let's take the time to first discuss bounded sequences, and then let's just come back to this. Bounded sequences. Not a very difficult thing to guess like what it is. Like just like bounded functions, a bounded sequence. Okay. So we can actually define it as upper bounded and lower bounded separately. Let's define upper bounded. And all it means is that there's some real number such that no term exceeds that. Okay? So P1 is bounded above if there is a real number n such that ai is less than equal to n for all I. And then similarly, we can define lower bounded. Similar. And then we can define bounded as both upper and lower bounded. There's some lower limit and some upper limit. But note that we can also define. Okay, so the lower and upper limits can be different, of course, and they should be different. But we can define it in such a way that they're just the negative of each other. I can just sort of be lenient with the boundary. Yep. Is this clear? So, first of all, bounded sequences need not converge, right? So, because something like 1 minus 1, 1 minus 1, 1 minus 1 does not converge. But convergent sequences are bounded. So, convergent sequences are bounded. Why?
Because they are in some like epsilon range of the number to which it's converging.
Well, but there are also some terms in the beginning.
Oh, okay.
What about those?
Okay, yeah. Let's consider that there is some least element, because there should at least be one least element or one biggest element in the sequence. So if there is a least element, we clearly have a lower bound.
Well, I mean, a sequence doesn't necessarily have a least element.
A convergent sequence must have it. Oh, no.
But you're close. It's not too far away.
But it necessarily not be bounded, right? Because let's just take the sequence which starts
No.
with like minus.
No. A sequence may not have a least element, but may converge. Like, for example, 1/2, 1/4, 1/8, 1/60.
Yeah.
It doesn't have a least element, but it converges.
It has a least element, and it
No,
converges.
it does not have a least
Oh, yeah. No, I mean like it's. Oh, okay, yeah.
I'll define a term which you're using for least element later.
Infimum, right?
Yes, it's called infimum. Yes.
Also, by bounded, do you mean like it has only one bound or both the bounds it should have?
A defined bounded term. Mod AI. So it's between minus m and m. So it has both lower and upper.
Yeah, but that's not necessarily true, right? Because let's just consider the sequence would start from minus infinity, comes all the way to 0.
What does it mean for a sequence to start at minus infinity? Because Sequences
give
are
me-
real numbers.
Can I tell you why they are not?
Yeah, just hold on.
So
You give me any
we have
negative
that,
number, the sequence which has there's a number which is less than that.
No, but you can't start from that, right? How do you start from it?
Oh yeah. So okay, I get the point.
can I tell now?
Yeah.
So we have by the convergence definition that for epsilon greater than 0, there exists some n such that all m greater than that, and have that modulo am minus a is smaller than or equal to epsilon.
Yes.
Yes. So we can see that as epsilon goes down, this an gets closer to a.
Sure.
So we can then get that modulo an is smaller than equal to a, is greater than equal to a.
That's not true. I mean, you can have a increasing sequence that converges back to it.
But increasing sequence, how can they converge?
-1, -half, -1/4, -1/8.
We are talking about modulo, I guess. Modulo I have said. We have a lower limit of modular AI.
Well, okay. So you can have 1 plus half, 1 plus half plus 1/4, etc. This is an increasing sequence that converges to 2. And the mods are also increasing.
So m is equal to 2.
Yeah, A is 2 here. Yeah.
We
I
can
think I
directly
have
see
a
as epsilon goes closer to 0. We have that some m get am gets closer to 2.
Mm-hmm.
So we get that some m gets arbitrarily large so that it tries to reach its peak or greatness.
AN doesn't get arbitrarily large here, right? AN is always less than 2 for all n.
It tries to get large so it can get more closer to 2 such that there exists some very small value of epsilon more greater than
Yeah.
0.
Yeah. Okay. So we have some epsilon such that eventually all terms are between in a small range around A. But why does this prove that this whole sequence is bounded? Like, I just want the finishing line.
Because that we have from the definition of convergence that all m greater than n will also have the same bound.
Yes. And what happened to the beginning terms?
The
Like
beginning
A1,
terms can
A2.
be. Can you give a minute to think?
I
Yeah.
got that. Shall I tell?
Yeah.
Okay. So let's say we first show that the sequence eventually goes only towards the right or to the left on the number line.
That's not true.
That's not true. Can you give an example?
1 minus half, 1/4 minus 1/8.
Like by right or left, I mean like let's
We
just
can
pick number
consider
3.
modulo.
Wait, sorry. Pranav, can you speak?
Yeah. Like consider number 3. It either goes to the right of 3 always or left of 3. I mean, 3 is not a good number to say. Okay, let's say we have A. A is the number to which it converges. Then we pick epsilon equal to 1. Then it at some point of time, it will only be in the range of epsilon, right?
Sure.
And before that, there are only finite number of terms in the sequence.
Yes.
And it's bounded. Finite sequence is always
Yeah,
bounded.
that's literally what I wanted to hear. That the beginning terms don't really matter because it's just a finite set of numbers. Yeah. So all we have is that all numbers eventually are in this range. And then other than these, we have only some finite numbers, right? I don't know, like 100 numbers or 1,000 numbers. Just take the largest of them and the smallest of them among these. These are just finite things. So these act as boundaries. Or maybe just add the sum of mods of them or something. Even that is fine. Anything like that. Anything easy. That's it. Yeah. Okay. So, okay, we did say that bounded sequences are not convergent, right? May not be. Need not converge.
Can I give an example?
I did give an example here. So,
Yeah. Oh, yes. Fine.
yeah.
I was just going to give the same example, by the way. I didn't remember that you just gave it.
Yep. But here's a theorem. It's sort of important, called monotone convergence theorem. So, an upper bounded non-decreasing. Non-decreasing means that each term is at least as much as the previous one. Non-decreasing sequence convergence. And there's an analogous theorem, like a lower bounded non-increasing sequence converges. So intuitively, what this is saying is, okay, I have some upper bound, right? And each term is like more than the previous one, or at least as much. So if that is not the case, then I could always have a sequence that goes down and then comes up and then goes. It looks, I'm making it continuous, but you get what it means. So this may not converge because it could oscillate between numbers. For example, minus 1, 1, minus 1, 1. But this is not the case here. Right? Each term is like at least as much as the previous term.
For example, we can take f of x is equal to 1 plus 1 by x raised to the power
Raised to the power?
x.
Yes. Yeah. That's a good example.
So I got a proof
The
of
upper
this.
limit is Euler's constant, I guess. I remember.
Sorry, what?
For the function, I said I guess the upper limit is Euler's constant, if I remember.
Yes. Yes. Nice. Yeah. So this sequence, for example.
Also, I got a proof for this theorem.
Wait. Let's let the other people see. Yeah.
Okay.
But even simpler than this would be something like 1 plus 1 over n. Oh, no, I mean 2 minus 1 over n.
Yeah, it's upper bounded by 2, right?
Yes. And in fact, it also converges to 2 in this case. But note that it may not converge to its upper bound. This upper bound could be here. 3 is an upper bound for 2 minus 1 over n, but the sequence doesn't converge to 3.
Oh, that sequence converges to 2 by that, like, consider the sequence 2, which is just a constant sequence, and then 1 minus 1 by n. Minus 1 by n converges to 0. So that an plus bn
Yes.
should converge.
Yeah. Or you can just directly show it as well. Yeah, sure.
Yeah.
Either way. Let's try to prove this. This is itself interesting.
Shall I tell?
No, let's wait.
Okay.
It's not that simple, is it?
I guess so.
Well, I mean, don't use the fact that Cauchy sequences converge. You can't use
I
that.
didn't even think of Cauchy sequence.
From that, it's sort of easy, relatively. But yeah, let's not.
Okay.
Yeah, it makes sense using Cauchy's.
Yeah, but don't use the Cauchy thing because
Okay.
we later prove that Cauchy thing using these properties.
Are we going to use this to prove Cauchy's?
I don't think Well, in some way, maybe.
Okay.
Here's an important property for real numbers. Important. Property of reals. It's kind of nice. It looks very obvious at first. So, suppose I have a non-empty set, and suppose S has an upper bound. Let's say S has a lower bound. Then there exists a real number S, which is the greatest lower bound. It makes sense to say something like greatest lower bound. So, what I mean by this is, for example, suppose you have the set of all positive real numbers. Right? It is lower bounded, right? It's lower bounded by -100, for example. But then we also have a greatest lower bound, right, which is 0. Because there is no bigger number which is a lower bound. So, for example, if I take S to be the set of positive reals, then 0 is the greatest lower bound. Does this make sense?
Yes.
The name is sort of obvious. Because among all lower bounds, there are many lower bounds, right? Every negative number is a lower bound, even 0 is a lower bound. And 0 is the greatest among all of those. Similarly, if a set is non-empty and upper bounded, then it will have a least upper bound. So we'll use this here. So do you see where it might be useful to use this? So remember that I sort of shifted this upper bound and said that there can be so many upper bounds. So do you see do you see where it will converge? Like,
To the lowest upper bound.
yes, yeah, that's the idea. And that's the whole that's the idea for this proof. The idea
Also,
is that
I think we can do this without even using this property.
okay,
Like
let's
it
share it.
somehow comes in that. Yeah. Oh, shall I tell you?
Yeah.
So let's just consider a upper bound. Let's just say it B, capital B.
Okay.
Then we pick a point in the sequence. It's at distance, let's say D.
From B. Okay, let me just draw this here. Yeah.
Yeah.
So I have some upper bound and I have some sequence. Okay, yeah. So I take a point and this is at distance
D.
D. Yeah.
Now, when we move to the right, this distance should either decrease or be constant.
Sure.
If it's always constant, it converges to that point,
Okay.
which is just B minus D. And
Okay.
if it like keeps on reducing, it can reduce at max to 0.
Well,
Like at some point, it will become constant, or it will go on to reducing till 0.
that's not true.
B is an
Because
upper
your
bound.
distance could be 1/2 to the n, right? Or rather,
Oh,
rather
the distance approaches 0.
well, okay. Rather, the distance could be half plus 1/2 to the n. What then?
Okay, the distance approaches to some limit,
Yeah, but
some number.
that's what we want. But basically now you're trying to prove that a sequence that you're trying to prove that a non-increasing sequence is converges, right? I mean, you're just trying to prove the other corresponding thing
Ah.
for the theorem.
No, but the thing is,
You're inside.
This distance is always greater than 0, we know.
Exactly. So you're saying that a lower bounded sequence, which is
Yeah, okay.
non-increasing, converges. You're using that to prove that. Yeah. So you can't do that. Intuitively, it makes sense now why the theorem is true, right? But still need to prove it. Yeah. Sorry, there was a comment. Extreme. Yeah. Well, I mean, it will use this greatest lower bound. So there is some sort of an extremal principle, if that's what you're talking about. We will use this fact that there is a greatest lower bound here. So here is the idea, right? So I'll try to write this down a little. First, let's just explain the intuition, right? So we know that the sequence has an upper bound, right? So consider the set of all upper bounds. This set is bounded below, right? So, okay. So let me write this well. So consider the set S of all upper bounds for the sequence of the sequence. First of all, S is non-empty because we already said that the sequence is bounded. Also, S has a lower bound. Why does it have a lower bound?
Because it is non-empty.
It is more than?
It is non-empty.
No, I mean, not all non-empty sets have a lower bound, right?
But they have, like, take the least element. That's the law.
Can you speak louder? I couldn't hear you.
Like all non-empty sets have a lower bound. We can take the least element there.
No, it's not a finite set. I mean, the set of
Yes.
all reals doesn't
Oh,
have a lower
yes. We are considering a real number set.
bound. Yeah.
I mean, if it doesn't have a lower bound and we keep on decreasing this S, then at some point it will intersect with the sequence and that won't be an
Yes.
upper bound.
Yeah. So, for example, A1 is a lower bound, right? Just the first term of a sequence is a lower bound, right? Like every element, like S is at least A1 for all S in S. Right? Otherwise, how could this even be an upper bound to the sequence? Because okay, so we have, so this is a non-empty set with an upper bound. Great. So since it's a non-empty set, sorry, with a lower bound, this implies S has a least element by this property of yours. It's a very nice property. It's called the completeness property. So S has a least element, which is the lowest upper bound, right? Least upper bound. Okay. Let's call this. Let's call this something. Let's call this A. Yeah. So what is this A really? What this A is that okay? I have an A.
We
which
want
acts,
this A to be limit an as intense.
Yes, I mean we'll show that this is indeed the limit. So clearly, okay, by definition, this is an upper bound, right? But suppose I decrease it very little, right? Suppose I decrease it by epsilon. Then A minus epsilon is not an upper bound by definition, right? Because
Yes.
A is the smallest upper bound. So anything smaller than that cannot be an upper bound, which means there is some term in the sequence that exceeds it, right? So this means no matter what epsilon I pick, there is some number n epsilon such that the sequence exceeds a minus epsilon. And note that this is always less than equal to a by definition of upper bound. And now eventually all terms will stay in this range. So this actually means that an
Now we
minus
can
a,
include the epsilon somewhere.
and this itself means that the limit is capital by definition of capital.
This was nice and very clever idea.
Yeah, this is very cool. Like, you need this property, which plays an important role. Note that this property is actually not true if we only take the set of rationals everywhere. So think about that. So it's particular for reals. Okay. So let me just write. The idea. For every epsilon more than 0, a minus epsilon is not an upper bound.
We can write it a minus epsilon does not cancel.
Sorry, what?
We can also write it in short as a minus epsilon does not laziness.
Yes, yeah. Yeah, because a is the least element. This implies that there exists some term in the sequence which exceeds a minus epsilon. But since the sequence is non-decreasing, it means that for all naturals at least n minus epsilon, a minus epsilon is less than an, which is less than equal to a. This is because upper bound, but this is just a way. This what is also true is that what is also true is this, and so the sequence converges to capital. Yeah, is it clear?
Yes.
So, great. By the way, this greatest lower bound is also called infimum. And the least upper bound is called supremum. Least upper bound is called supremum. This is different from max and min because you may not achieve the max. For example, 0 is the infimum of the set of all positive reals, but 0 is not the min of the set of all positive reals. There is no minimum. Okay, great. Finally, okay, we have time for just 2 more exercises and then I think I will have to leave after that. Okay. Here is another cool theorem. Prove that every bounded sequence has a convergent subsequence. By bounded, I mean bounded both below and above.
Can I tell?
Let's wait for some time. I want others to try as well. So, I mean, feel free to speak, please. It's fine if it's wrong. It doesn't matter really. Yeah, you had ideas, Anurag?
So my idea is to like either take the non-decreasing part or take the non-increasing part.
Why does such a part exist? Good idea. Yeah, that's the idea, in fact. So here's so this will actually follow from.
So
Let me just write that down. Follows from this. Every sequence has a monotone subsequence. By monotone, I mean either constantly non-increasing or constantly non-decreasing. So if you can show that, then note that the previous theorem combined with this finishes the problem. Right? Yeah, go on.
so we have it because like uh, we have two bounds. So either for some AI it is greater than some. So we have that let the lower bound be some A and the upper bound be some B. So we have AI is smaller than equal to A and it is greater than equal to B.
Okay. So okay, we're talking about bounded sequences. So we have some lower bound minus a, okay,
Yes,
plus a, and upper bound plus b. Yeah.
yes. So we have that this here. All the terms of the sequence lie between in this interval only.
Sure.
So either this interval is a pure constant. So if it is a
Okay.
pure constant, we can take the whole sequence, and it
Yeah.
is already a converted sequence. Or it
Yes.
is like only increasing and decreasing again and again.
Okay.
So we can take like it is minus one plus one minus one plus one. So we can take like minus one only outside.
Okay.
So we have that convergence of sequence. For like some oscillating sequence like minus one plus half, minus one by four, plus one by eight, we can take the any of the part.
Yeah, but exactly what? Because it's not clear what exactly you're taking. Okay, so the proof of this theorem has an idea that I've seen in another Olympiad problem actually. So it's quite cool. I'll try to find that Olympiad problem and give it to you the next time.
Are you saying Eto's theorem?
No. That's different. It's a different. It's more of an algebra problem actually. But you can use no. Maybe.
It is a real number. But where it should work.
Yeah, but it only proves that uh, every sequence has a monotone subsequence of arbitrary length. It doesn't show
Yes, it shows for a finite number.
Yeah, it just shows that for any number n, I can find a subsequence which is monotone of that length, but it doesn't show infinite. So you're right.
Yes.
But I think you can sort of use that idea to come up with uh, the same thing, if I think about it.
Becomes like the infinite pigeonhole principle. Like the
Sort
numbers
of.
get larger, so the subsequence also gets larger. So if it reaches infinity, the subsequence will also reach infinity in some sense. If
Yeah.
we don't consider rigor at all.
Yeah, but it doesn't exactly work. Maybe
Yes,
if I think about it. Yeah. Okay, so think about these. Okay, so suppose I have this sequence.
I think I got the idea.
Yeah, tell me.
It's a bounded sequence to consider the minimum upper bound.
Okay.
Now you can just pick a sequence. Oh, that does not converge necessarily, right there. Yeah.
Because the sequence need not converge.
Yeah, like if the lowest bound is let's say 3, then it's possible that no, wait, it should converge.
It could work. I mean, I can see a proof along the lines of what you're saying. Well, actually, maybe not. Yeah, maybe not. Never mind.
If we don't consider the order, then there are also use subsequence.
Could you say that once more?
But we are also considering order there. If we didn't, we can easily get some subsequence.
Yeah. Yeah, it's not to do that. Yeah, never mind. Yeah, I mean, this is not terribly. Actually, try this thing more. Every sequence has a monotone subsequence. Forget boundedness.
Okay, so we can start from a point, and then first let's just consider all the points which are greater than the previous point. So like you can try to find a monotonic increasing sequence first.
Okay, so
wait, monotonic means non-decreasing or strictly increasing?
Non-decreasing or non-increasing, either.
Yeah, okay.
Because
So
otherwise the constant sequence is a counter.
Oh yeah. So let's first try to find a monotonically increasing sequence if it exists.
Okay, so we start with the point.
Yeah, and we go, and whenever we encounter a point n greater than or equal to this thing, we just pick that.
Okay.
And we continue this thing.
And suppose we get stuck.
Yeah. If we get stuck, we know that this is the largest point which exists.
Yes.
Now pick this point and just continue to go down.
Okay, so let's say we pick some point here.
Yeah.
Then
we just try to pick a like monotonically decreasing sequence, right?
Okay.
Because if there exists some
okay, and suppose we get stuck, then
Why will we get stuck?
Why not?
We have a lower bound, so we can get
Oh, we can have a lower and upper bound, right?
We could get stuck. But
Oh,
you're
so
close. Don't consider a decreasing sequence. Start thinking of an increasing sequence again.
we can just pick the points.
So
Yes.
so first of all, note that no term, no term will ever reach here, right?
Yeah.
Because this is now an upper bound for the sequence eventually.
Yes.
Okay. So now let's start finding an increasing sequence again.
Okay.
Can you go on with your suggestion? Just think about what to do next. Exactly what you were doing before.
Can I
We-
continue?
Yeah, Anurag?
So either it converges to that largest point, or it keeps increasing,
It doesn't have to converge. Right?
or it gets at a, or it gets stuck at a point, and it starts to get down again.
Yeah, so suppose we cannot go further up. Then this means
So we mark this point, and if some point goes greater than it, we will take that in our increasing subsequence.
yeah, I mean if we're stuck then there will be nothing greater than this eventually. Right?
Yes. So
Oh, yeah.
if we get stuck, we can get a we can mark this as the second largest.
Yes. And then
We can
start
draw a
again.
line here. Yes, we can start again.
Exactly. Okay. So here is the idea. Yeah, this is right. So we start with a point and look for a non-decreasing sequence. Yeah. And we keep going up. And suppose at some point we get stuck because there is nothing which is greater than or equal to it. Then we mark this point as special. And then we restart. We restart from the next point. Then again we look for non-decreasing subsequences starting from this point. And if we don't get stuck at a point, and if then we're done really, right? Otherwise, if we get stuck, then mark this point. You can mark this point, etc. And then if we get stuck every time, then this sequence works because this is a non-increasing sequence. So either one of the white lines will work or this peaks will work. So, okay. So here is the idea that, yeah, just formalize this. I can write this formally, but just leave it up to you. And yeah, so let me just put a bunch of questions that you can try on your own. Just go back to showing that Cauchy if and only if conversion. And you can just in general try to prove other identities like for sequences, for example, sum of convergent sequences converges to the sum of the limits. You can also show it for product. You show it for differences obviously. And ratios if and only if the second ratio is non-zero. Then yeah, something like this. And maybe let me just try to find a question which is nice. It's hard to find interesting questions. Okay, so this is nice. So you can try these two questions. Suppose A1, A2 converges. Show that okay, rather suppose okay, so instead of taking sequences, what I will do is I will consider. Okay, so I have this sequence A1, A2, A3 is a sequence, and then I can consider the sequence B1 defined as A1, B2 defined as A1 plus A2, B3 defined as A1 plus A2 plus A3, etc. Right? So it's just the sum of the first k terms. Right? And here's the question: prove that if B1, B2 converges. Okay, I should write it down properly. So we say that summation an converges to A if Bn tends to A. Basically, instead of the sequence converging, this notation is used to say that the sum of the first n terms is converging. For example, this sequence, if this is the sequence, then note that an converges to 0, but summation an converges to 2. Note the difference, because summation an is the convergence of the sum of the first n terms. Okay, so prove that if summation an converges, then so does.
This one just follows by Cauchy, right?
No,
Like
I'm not saying that an converges if and only if bn converges or something like that. That's not even true, actually.
I mean, sigma an sequence is just the sequence Bn, no? What's the difference?
Yeah. It is. Yeah. I mean, I'm just telling you the definition of this.
Oh,
Say
okay.
that-
I thought you were gonna say then so does A.
Well, no, so does B, you mean, but that could be obvious.
No, like if sigma an converges, then sequence A also converges, right?
Yes, that is true.
Yeah, I
Why?
thought you would ask this in this
No,
question.
actually, is it that obvious?
Yeah, like if sigma n converges, then sequence B is converging. So by Cauchy, we get that the conjugative differences would be like constantly decreasing or something.
Well, that's not what
Monotonically
Cauchy
decreasing.
says.
But
That's not
it
what
is not bounded.
It's bounded, yeah.
But
Yes,
it
it's
is true that
bounded by
if
zero.
if summation an converges, then an actually converges to 0 always. That is true. But yeah, that's not what I'm asking. I'm asking this.
This looks bad.
I'm assuming all an are positive, non-negative.
Also,
So
by n is like outs. Never mind, I'm high.
yeah,
What?
this. So
Yeah,
so basically, I'm saying that if A1 plus A2 plus A3 up to so on has a limit, then so does root A1 plus root A2 by 2 plus root A3 by 3 plus etc. So this will be nice, and just one more copy. So um, suppose A1, A2, A3 is a non increasing sequence of non-negative pairs. I'll just post a screenshot of the questions on Discord, by the way. Prove that. This is just in case I don't make something like that. So prove that summation an converges if and only if summation um, 2 to the n times a 2 to the n. So let me tell you what this means. I have a sequence of non-increasing numbers of non-negative reals. So I'm saying that show that this has a limit if and only if 2a1 plus 4a2 plus that's not right. Well, you can take n at least 0. Doesn't matter wherever you start from. You can start from 1. Fine. 2a2 plus 4a4 plus 8a8 converted. Just as a corollary, just an interesting observation. Note that if you take ai to be 1 over I, then what does this say? It says that this sequence converges if and only if what is a1? A1 is 1, 2a2 is also 1, 4a4 is 1, 8a8 is 1. Converges.
He's
Obviously,
short. Like,
yeah.
try-
Yeah, 5 minutes more.
Sure.
So clearly this is false, and hence this is false. And therefore this actually diverges. And if you know this from before, it's true. If you've seen this before.
There is another way to prove this, I guess.
The
So
other proof is
I
nicer.
It's that proof of 1/3 plus 1/4 is more than half thing, right?
Yeah.
Yes.
That's exactly what you need to prove the question, actually. It's the same thing. So note this thing. It's exactly the same thing. You're accumulating 2 to the n terms. Yeah, it's the same proof. So that proof actually is inspired from this question. So it's not someone who magically thought of it directly. I'm pretty sure someone thought of
I
this.
guess it was given to give some easy proof.
Yeah, so just try this. It's nice. So you know the proof of that. Just do the proof of this in the same way, except bounded on both sides. So, like for the proof of this, you do this, but here you should also do something like this is more than. What should I say? Maybe I should. Like if you do something like 1 more than 1/4 plus 1/5 plus 1/6 plus 1/7. So if you divide by 2, then I
This
can
makes a better sense.
make it like this. And then similarly 1/4, 1/5 plus up to 1/8 is more than half. And that is more than 1/8 plus up to 1/15 over 2. And then add these. So that's how you'll get this on both sides. And so that's how you'll get if and only if. Yeah. Okay, so questions? I'll try to post more of the problems. I'm just taking most of them straight from the book. That's the book by Rodin. You can try the problems if you want to. Just write it down.
I'll end the recording.
Yeah.